Hello everyone. In this lesson, we are going to learn the Gauss-Jordan method or the Gauss-Jordan method. The Gauss-Jordan method is a method for solving linear systems, and this method is quite well known because it will always give us the solution set for a given linear system. Not only that, this method can also determine if a given linear system has a solution or not. So to begin, we first recall some result from the previous lesson. So here you get two linear systems denoted by heart and diamond, and that the linear system heart was obtained from the linear system diamond by performing any of the following operations. Either you swap two equations from the linear system, or you multiply an equation or both sides of an equation by a non-zero scalar, or you replaced one equation by its sum with a scalar multiple of another. According to the theorem, the resulting linear system is equivalent to the original one, meaning to say they both have the same solution set. Therefore, if you can solve the linear system heart, then that is equivalent to solving the linear system diamond. Usually, the reason why we perform these operations on a linear system is to get a new linear system where the solution can easily be observed or can be solved by back substitution. That is why we were motivated to study the row echelon form of a matrix and the reduced row echelon form of a matrix. Remember that a linear system may be represented by its what do you call this? The augmented matrix. Now, the augmented matrix is a matrix containing all the coefficients of the linear system arranged in rows and columns, thereby performing operations on the equations will affect the rows of the given augmented matrix. So here are the Gaussian operations in terms of matrices. We call these operations as elementary row operations. So there are three types of elementary row operation. We have the type 1, 2, and 3. The first type corresponds to swapping two equations in a linear system. In terms of augmented matrix, that corresponds to swapping two rows of a matrix. So when we swap row I and row j in a matrix, we denote that operation by E subscript ij. The second type corresponds to multiplying an equation both sides by a non-zero scalar. Therefore, correspondingly, when we do that operation, we actually multiply every entry in a row by the non-zero scalar. So if we multiply the row I of a matrix by a non-zero scalar alpha, we denote that operation by the symbol EI alpha. The I here represents the row number where we are going to multiply the scalar alpha. Take note again that alpha cannot be 0. The third type of elementary row operation is the one where we replace a row by the sum of it and a multiple of another. So if we replace row I by its sum to alpha times row j, then we denote that operation by Eij parenthesis alpha. The I denotes the row to be replaced, j denotes the row to be multiplied by the scalar alpha. The resulting sum of the two rows will be placed on the ith row of the new matrix. Now, if a matrix B was obtained from a matrix A by performing a finite number of elementary row operations, any of these, we say that A is row equivalent to B. And we express this by writing A tilde B. Or we simply read A is row equivalent to B. If an elementary row operation E, any of these, was applied to a matrix A obtaining a matrix B, in terms of diagram, we denote it by putting an arrow from A to B, going from A to B, and then putting the name of the operation above the arrow. This is just for a notation purpose, or purpose of having a good notation. So for example, we have the following three matrices on the board or on the screen, and it is indicated that we are going to perform these elementary row operations on each of these matrices. So how do we do that? So first of all, the first operation here is a type 1 operation where we interchange two rows. Again, the symbol E12 represents a row swapping of the first row and the second row. So what we do is we simply swap the first row and the second row as follows. So the second row will now be the first row, while the first row will now be the second row. And there you are. There we get the answer. So it's easy, right? Alright. For the second operation here is a type 2 operation. Here, we are multiplying the second row by the scalar -3. So how do we do that? So what we do is we simply copy the first row as it will not be changed at all. Now we multiply -3 to every entry in the second row, so -3 times 3 is -9, -3 times 4 is -12, and -3 times 0 is 0. For the third operation is the type 3 elementary row operation. Again, the meaning of this is that we will replace the second row. Now, when you look at the first index, we will replace the second row by its sum with -3 times the first row. So in order to do this, because we will only replace the second row, we just copy all other entries unchanged. Now, so we will just copy the first row because it will not be changed anyway. Now, how do we get the entries of the new second row? So what we do is we multiply -3 to the first row and add it to the second row. So -3 times 1 is -3 plus 3, you get 0. So as you can see, the effect is that we have just made this entry 0 after doing this operation by multiplying a -3 here, and then add it to 3. Now next, -3 times 2 is -6 plus 4 is -2. Is that correct? Now you can always pause and rewind if you find this quite fast. If you find that some computations are incorrect, you can always comment, or you can send me a message on our Google Classroom. The last entry will be -3 times -1 plus 0, and that is 3. So easy, right? The next example asks us to find a matrix in reduced row echelon form, which is row equivalent to the given 4x4 matrix. So by this example, or by this exercise, we mean we need to perform a sequence of elementary row operations in order for us to result into a matrix in RREF. Again, to recall, a matrix is in RREF. There are 4 conditions. Number 1, if there are 0 rows, they must appear at the bottom part of the matrix. Second, to each non-zero row, the first non-zero entry from the left is a 1, and these ones are called the pivots, right? Third condition is that these pivots should appear in an echelon form, meaning to say they are in a ladder form. Last but not the least is that for every column that has a pivot, no other entry, no, aside from the pivot, are non-zero. So dapat lahat ng entries na nasa column kung saan may pivot, maliban sa pivot, ay 0. So how do we perform this one? I want you to listen carefully because this is algorithmic in nature. So the first step is to just write down the matrix 0, 2, 1, 3, 1, 2, 1, 3, 1, 0, 1, 1, 1, 6, 0, 6. You can write by columns or by rows. It doesn't really matter. So the first thing that you need to do is, because there are non-zero entries in this column, you wanted to have a pivot over here, or you wanted to have a 1 here. Surprisingly, there is a 1 there. So I can just swap the first and the third row to move the 1 there. But if there are no 1s, you can, for example, swap with the second row and then you get a 2, then apply a type 2 operation by multiplying a 1/2. So it depends on you. Right? So first, for example, we can swap the first and the third row as follows. So the first row will now be 1, 1, 1, 0. Second row will just be the same. The third row will be 0, 1, 1, 0, 1, 1, 1. The fourth row will not be changed at all. Alright? Now that we get a pivot over here, the next goal is to zero everything under the pivot, or to zero everything else that are not zeros in its column. And to eliminate or to zero out elements, what we really want to apply are type 3 operations. Now, for example, in order to zero the second, the number 2 here, or the entry 2 here, using the pivot is in the first row. So because we wanted to eliminate the 2 over here, what we want to do is to multiply the pivot by -2 and then add it to 2 to make this 0. So that operation corresponds to a type 3 operation, e21 -2. Again, the symbol e21 -2 stands for replacing the second row by its sum with -2 times the first row. So the row that you are going to replace is going to be the first subscript. The row where the pivot is going to be the second subscript. And the scalar over here is the scalar that we're going to multiply to eliminate the entry. To eliminate meaning to make it 0. At the same time, because there are 2 entries in this column that we wanted to eliminate, we can perform 2 type 3 operations consecutively. So to eliminate the entry here using the pivot 1 on the first row, what we do is we apply the type 3 operation e31, 3 because we're going to zero out the entry on the third row, 1 because the pivot is in the first row. Now the factor that we're going to multiply to the pivot to eliminate the entry 3 is going to be -3. So we're going to perform this consecutively. We can do this to save time, and that will not really change the result. You can do it one by one, but if you can do it simultaneously, that's better because it will save you time and effort. So we just copy the first row. Now the second row will be as follows: -2 times 2 plus 2, of course that is 0 because that is the goal. Next, -2 times 1 plus 2 is also 0. Next, -2 times 1 is -2 plus 0, that is -2. Next, -2 times 0 plus 6 is 6. Do you follow? you can always pause and rewind if you happen to miss out something. I'm sorry, something is wrong over here. The 3 that's going to be eliminated is not on the 3rd row, it's in the 4th row, so that should be a 4. Okay? I'm sorry. So the 3rd row will not be changed at all. No, it's going to be 0, 1, 1, 1. Then the 4th row will be changed. Now, of course, this will be 0 because that is the goal. That is the reason why we have this operation. In fact, that's negative 3 times 1 plus 3. That's why we get 0. Next, negative 3 times 1 plus 3 is also 0. Next. Negative 3 times 1 plus 1 is negative 2. Finally, negative 3 times 0 plus 6 is 6. Alright, now we now have a pivot on the first row. Alright. Now the next, because the second row is non-zero, we wanted to have a pivot on the second row. Right? You can, well, as you can see, for us to have a pivot on the second row, the first non-zero entry from the left must be a 1. So what you can actually do is you can multiply this entire row by negative 1/2, for example, to make a 1 over here. That is an option. Or you could actually swap with the third row, because I can see that there is a 1 on the third row. So I can just swap with the third row, so I can move the 1 over here. So let's try to do that instead. So it's going to be 1, 1, 1, 0, 0, 1, 1, 1. Then, what else? The second row will be 0, 0, negative 2, 6. The fourth row will just be the same. Alright. Now we get a pivot on the second row. Surprisingly, the entries below it are all 0, but there happen to be a 1 above it that is not yet 0. So actually, we can perform a type 3 operation to eliminate the entry 1 written in asterisk. No? So, what I can do to eliminate that is I can multiply, because this is the pivot is in the second row, I can multiply the pivot by negative 1 and add it to 1. So that corresponds to the operation. Of course, we will replace the first row, the pivot is in the second row, we will multiply a negative 1 on the pivot. Alright, so that's 1, 0, then negative 1 times 1 plus 1 is also 0. Diba? Negative 1 times 1, negative 1 plus 0 is a negative 1. Then I will just copy. Like so. There, I get now two pivots over here, this one and this one. The next is we wanted to have a pivot on the third row. So we wanted to make this a 1. So in order for me to do that, I can make a type 2 operation. I can multiply the third row by negative 1/2. Okay? So it's going to be 1, 0, 0, just copy. Except the third row. The third row will be 0, 0, 1, negative 3. Is that correct? Now there you get a pivot on the third row. So, wait a minute, I'm going to encircle the pivots for you to see. What is it that I'm using to eliminate? Alright? So 1. So I wanted to eliminate this one and that negative 2. So to eliminate, I'm going to use a type 3 operations. So to eliminate the 1, I can replace the second row. The pivot is the third row. I can multiply the pivot by negative 1. To eliminate the negative 2 in asterisk, I should replace the fourth row. The pivot is in the third row. We multiply the pivot by 2 by the additive inverse and get the following as a result. 1, 0, 0, negative 1. The second row will be replaced because below these guys are already 0, so nothing will really happen to this. Sorry. It will become 0, 1, then negative 1 times 1 plus 1 is also 0. That's the goal, in fact. Negative 1 times negative 3, that's 3, plus 1 is 4. Next, the third row will just be the same. The fourth row will be 0, 0. Because these are zeros, these guys will not be changed anymore. Okay? So we multiply these two to the pivot, add it to negative 2. Of course, that's 0 because that was the goal. Next, we multiply these two with negative 3. That's negative 6. Is that correct? Alright, 2 times negative 3 is negative 6 plus 6 is 0. So we ended up in a matrix like this. You see that the fourth row is contains all zeros. Therefore, that is a 0 row, and that's at the bottom part of the matrix, so that should not be a problem. So I think at this point, the matrix is now in RREF. So, as a result, this serves as an answer. So this matrix is in RREF, and it is row equivalent to the original matrix, as this was obtained from this matrix by performing a successive a sequence of elementary row operations. In general, we can, using this algorithm, we can always put a matrix, or we can always find a matrix from that is row equivalent in row echelon form, that is row equivalent to A. Furthermore, we can always find a unique matrix in reduced row echelon form that is row equivalent to A. This is the reason why we prefer the row echelon form over the row echelon form, meaning to say a matrix can be equivalent to many matrices in row echelon form alone, But if we insist to get a matrix in reduced row echelon form that is row equivalent to A, then there is only one answer. The uniqueness is guaranteed by the algorithm that we are performing. And consequently, we have the following theorem as a result. If A and B are the augmented matrices of two linear systems respectively, and A and B are row equivalent, then A and B are row equivalent if and only if the linear systems are equivalent. Meaning to say, doing row operations on the augmented matrices doesn't really change the solution set. Therefore, we have the following method known as the Gauss-Jordan method. So to perform the Gauss-Jordan method, we first set up the augmented matrix of the linear system. Next, we reduce the matrix A in its RREF, or we find the matrix B in RREF that is row equivalent to A. By how do we do this? By simply applying a sequence of elementary row operations. Just the algorithm that I have already shown you. Finally, the resulting matrix in RREF will correspond to a linear system that is in row echelon form and therefore can be solved by back substitution. That's it. That's the Gauss-Jordan method. So I have here 5 different examples, different sizes of matrices where we can try applying the Gauss-Jordan method. For example, this matrix, this linear system is 2 by 2, by the way. So the augmented matrix of this linear system, reading it in terms of rows, 1, 2, lagyan natin ng bar, minus 1, 4, negative 1, 5. Okay. Next step is to reduce this matrix. Just ignore the bar, no? Or this bar. This bar is just an imaginary line separating the constants over here, no? On the right hand side and the constants on the left hand side. So the next step is to perform a sequence of elementary row operations to obtain a matrix in row echelon form. So to do this, first we create a pivot on the first row. So there we already have a 1. So what we now do is we eliminate the 4 because we don't want any other thing aside from 0 in the column containing a pivot. So to eliminate the 4, we perform a type 3 operation. We're eliminating 4 in the second row and the pivot is in the first row, and we wanted to multiply a negative 4. So the resulting the resulting matrix will be the following. This will be 0, no? Negative 4 times 2 plus negative 1, that's negative 8 minus 1, that's I think negative 9. Is that correct? Is that correct? Negative 4 times 2 is negative 8 minus 1 is negative 9. Alright. Negative 4 times negative 1, that's 5 plus 5, that is 10. So this is now your matrix. Now we wanted to get a 1 or a pivot on the second row. So we wanted to make this a 1. So what we can do is we apply a type 2 operation. We can multiply. Now kapag gumagawa tayo ng pivot, tatandaan nyo, laging type 2. No? When we move rows, of course, type 1. When we make entry zeros, we apply type 3. Okay? So we wanted to multiply the second row by negative 1 over 9 in order for us to have something like this. Negative 1 over 9 times negative 9, that's 1. Then this will be negative 10 over 9. I hope my computations are correct. Kapag nakakakita ko ng mga fractions like 10 over 9, kinakabahan ako as if I'm doing something wrong. You see, I think I spotted an error. I'm sorry because I'm doing the computations here live. So the mistake was made, no, when we have done this one. Negative 4 times negative 1, that's a 4, no? I don't know where I get the 10. Negative 4 times negative 1 is 4 plus 5. This should be a 9. Okay? So you don't have to do this thing. Yeah, this is still correct. But this one should not be negative 10 over 9. Rather, it should be a negative 1. Now that we have obtained a pivot over here, we don't want anything in its column that is not 0. So we wanted to eliminate the 2. To do that, we again apply another type 3 operation, E. We're going to replace the first row. The pivot is in the second row. We're multiplying a negative 2 on the pivot. So therefore, obtaining the following 1, 0, that's the purpose. Negative 2 times negative 1, 2 plus negative 1 is a 1. Right? Then you get 0, 1, negative 1. So I think at this point, this is already in RR EF. Right? Because if you look at the pivots, no other elements below it and above them, no, are non-zeros. They are all zeros. So already this is in RR EF. So as you can see, the first column corresponds to the variable x. The second column corresponds to variable y. These are the constant. So therefore, the conclusion is that this linear system, the original one, is equivalent to the following linear system. X plus 0, y equals 1, so that means x is 1. 0, x plus 1y, so that's y, is negative 1. In fact, this gives us a unique solution for the linear system. The linear system has a unique solution, and that is the ordered pair 1, negative 1. Okay, let's try another one. So we first convert this into an augmented matrix. There you are. This is the augmented matrix. We next look at the first row. We need to make a pivot here. Luckily, we have a 1 over here. So we just wanted to eliminate everything below it using two type 3 operations. No? The first operation, we wanted to eliminate the 1. So we wanted to eliminate the 1 on the second row. The pivot is in the first row. We multiply the pivot by negative 1 to eliminate the 1. The second type 3 operation is that we eliminate 3 on the third row, right? The pivot is the first row, and we wanted to multiply the pivot by negative 3 in order to eliminate the 3. So the resulting matrix will be as follows. So that's to eliminate. Of course, this one is already eliminated, right? Next, negative 1 times 2 plus 3, that's a 1. Next, negative 1 times negative 1 plus 1, that's a 2. Negative 1 times 3 plus 5, that's a 2. Is that correct? Alright, negative 1 times 3, that's negative 3 plus 5, 2. Alright. Third row. Of course, this is going to be eliminated. Next, negative 3 times 2 plus 8. The pivot is in the first column, right? Negative 3 times 2 plus 8, that's a 2. Next, negative 3 times negative 1, that's 3, right? Plus 4, that's 7. Finally, negative 3 times 3, negative 9 plus 17, I think that is 8. I hope this is correct. So as you can see here, we have already formed a pivot on the second row. What we wanted to do next is to eliminate everything in its column, aside from itself, right? By doing type 3 operations once again. The type 3 operations are E1, 2, negative 2 to eliminate these 2, and to eliminate these 2, how do we do that? E3, 2, negative 2. So you can pause and think about these operations, kung paano naisip, bakit ganyan, kung saan yung i-delete, kung saang row yung i-delete, yun yung first index. Kung nasaan yung pivot, yung second index. Kung anong i-multiply sa pivot bago i-add, yun yung nandoon sa loob. Okay? So, I think, let's move this a little bit para magkasya. Sige. So, first row, what will that be? 1 na ito. Kasi 0 lang naman yung nandito. Kopya na lang. Ito magiging 0 ito because that's what we wanted to do, really. Next, we multiply negative 2 times 2, negative 4, plus negative 1, that's a negative 5. Last but not the least, in this row, negative 2 times 2, negative 4 plus 1, negative 4 plus 3, that's a negative 1. Second row will just be retained. How about the last row? Negative 2 times 0 plus 0, of course that's 0. This will be 0 kasi that's the goal. Negative 2 times 2, that's negative 4 plus 7, that's 3. Is that correct? Alright. Negative 2 times 2, negative 4 plus 8, that's a 4. Alright. Okay, we now look at the third row. We wanted to have a pivot on the third row. This is a 3, so we apply a type 2 operation. We wanted to multiply the third row by 1/3. So if we wanted to make a 1, we apply a type 2. So, there. Okay? Alright, that's me applying the type 2 operation A3 1/3 on the matrix. Now, because that we have a pivot over here, what we wanted to do is eliminate these two entries by applying two type 3 operations. To eliminate negative 5, we use this pivot. Alright, negative 5 is in the first row, the pivot is in the third row. The multiple is 5 in order to eliminate negative 5. So, additive inverse. Okay? To eliminate 2, so what do? We eliminate the one in the second row, the pivot is in the third row. We multiply negative 2 to the pivot. So we get the following. 1, 0, 0, that's the goal. We wanted to eliminate that really. Okay, here. 5 times 4/3 times negative 1. What is that? Scratch tayo, scratch. 5 times 4/3 minus 1. That is over 3, that's 17/3. Is that 17/3? Is that correct? Okay. Second row. 0, 1. This will be 0 because that's the goal. To get this one, to get that, we multiply we multiply negative 2 times 4/3 plus 2. So what do we get? This is negative 8/3 plus 2. So this is negative 2/3, I think. And the last row should be this one. So at this point we are done because this matrix is already in RREF, right? Again, the first column corresponds to X, second to Y, third to Z. So what we see as a result is that therefore X, Y, Z are 17/3, negative 2/3, 4/3. I think this is the correct answer. Again, this linear system has a unique solution. Again, if you miss out anything, you can always pause and rewind the video. Okay, let's move on to the next example. Again, this is a 3 by 3. So we first write down the augmented matrix. So this should be that 4, 5, 6, and then lagyan natin ng guhit 2, 3, 7. So for to simplify things out, now to reduce the stress of writing down brackets, like this, at first you can eliminate it, so you can reduce the time of writing. Okay, so here surprisingly there is already a pivot on the first row again. So what we are after to is to eliminate the things below it, okay, by applying type 3 operations. Eliminating the 2, that means E2, 1, negative 2, because 2 is in the second row, the pivot is in the first row, and the additive inverse of 2 is negative 2. That is to eliminate the 2. The second type 3 operations that we're going to perform is E3, 1, negative 3, because we are going to eliminate something in the third row. the pivot is in the first row, the multiplier should be a -3, the additive inverse. So the resulting matrix will be, the first row will not be changed at all. This will be 0. Okay, again, -2 times -2, that's 4, minus 3, that's a 1. -2 times 4 plus 5 is -3. I hope this is correct. -2 times 4 is 8, plus 5 is -3. Next, -2 times 2. Alright, -2 times 2 is -4, plus 3 is -1. Next, -3 times 1 plus 3, of course, that's 0. That's the goal. Then, again, -3 times 2, -2, sorry, that's 6, minus 4, that's 2. Next, -3 times 4 is -12 plus 6, that's -6. Next, -3 times 2 is -6 plus 7 is a 1. Next, we wanted to make a pivot on the second row. Luckily, we have a 1 over here, so what we wanted to do is to eliminate these things out. So we perform two operations, type 3 operations. What are the operations? Eliminating -2 on the first row, that's E1, 2. The pivot is in the second row. Additive inverse is 2. To eliminate these two, what we really wanted to do is E3, 2, -2. Okay, you can ask yourself why. You can pause and rewind. Okay, performing this operation, so we obtain 1, 0. That's going to be 0 because that's going to be eliminated anyway. 2 times -3 is -6 plus 2. Then 2 times -3 is -6 plus 4 is -2. Next, 2 times -1, -2 plus 2, that is 0. Second row will just be copied because the pivot is there. Next, the third row will be changed. No, it will be 0, 0. That has to be eliminated anyway. Next, -2 times -3 is 6 plus -6. That is 0. Alright. Next, -2 times -1. -2 times -1 is 2 plus 1, you get a 3. Okay? At this point, I would like to emphasize that we should stop the algorithm. And we already have a conclusion about this linear system. Why? If you look at the third row, of this matrix, where's the third row? The third row of this resulting matrix corresponds to the linear equation 0x plus 0y plus 0z equals 3. And as you can see, this equation has no solution. Do you remember the degenerate cases? Yeah, because this can never be satisfied, no? For any x, y, and z, this can never be satisfied. Therefore, the linear system itself cannot be satisfied by any vector because it has to be every equation in the system has to be satisfied. Because we know that this can't be satisfied at all. Therefore, as a conclusion, the linear system is what? Is inconsistent. Or you can say has no solution. Or if you are asked about the solution set, how do you write the solution set? The solution set is what? The empty set, because it has no solution. So that's how you know when a linear system has a solution. If there appears a row where to the left of this line you get all zeros, and then on the right you get a non-zero thing, you know that that equation cannot be satisfied, and therefore the linear system cannot be satisfied as well. So that's how you know when this magic row, a row something like this, appears. Okay, let's move on to the next example. So this is now a 3 by 5 linear system. We have 3 equations and each in 5 unknowns. So we first write down the augmented matrix of this linear system. So there, as you can see, this already serves as a pivot for the first row. So you wanted to highlight this pivot, and using this pivot we wanted to eliminate 2 and 1 from using the pivot. So we apply a type 3 operations, which are E21 negative 2 and E31 negative 1, and get the following as a result: 1, 2, negative 3, negative 2, 4, 1, 0, right? Negative 2 times 2 plus 5, that's a 1. Negative 2 times negative 3, that's 6, minus 8, that's negative 2. Negative 2 times negative 2 is 4, minus 1 is 3. Negative 2 times 4 plus 1 is negative 2. Is that correct? Let me just check it for a while. I think it's correct. Last entry, negative 2 times 1 plus 4. I think that's a 2. Third row. Oh wait. Third row, this is going to be 0. So by multiplying a negative 1 here and then add there, by multiplying a negative 1 here and adding it there, we actually just mean subtraction, 1 minus 1. Pag ganon. Okay? So basically, that's just 0. 4 minus 2 is 2. Negative 7 minus negative 3 is negative 4. Next. What's next? 5 minus negative 2 is 7, I think. Is that a 7? Then 2 minus 4 is negative 2. 8 minus 1 is 7. I hope this is correct. Next, we wanted a pivot in the second row. This one is a good one. We just eliminate these things out. So we apply type 3 operations once again. E12 negative 2 and E32 negative 2. Again, the pivot is in the second row, so the second subscripts must be a 2. Alright, so rewriting the first row, 1, 0, because that is supposed to happen. No? Next, we multiply a negative 2. Negative 2 times negative 2, that's 4 minus 3, that's a 1. Negative 2 times 3, negative 6. Is that correct? Negative 2. Sorry. So let me first write the second row. Naguguluhan din ako. Alright. I think that's it. Negative 2 times 3 is negative 6. Negative 2 times 3 is negative 6. Plus negative 2 is a negative 8, I think. Is that correct? Ulit, negative 2 times 3 is negative 6 plus negative 2, that's a negative 8. Okay. Negative 2 times negative 2 is 4 plus 4 is an 8. Negative 2 times 2, that's negative 4 plus 1, negative 3. Then here you get 0, 0 because that has to be eliminated. Next, we do the following. Negative 2 times negative 2 is 4 plus negative 4, 0. Negative 2 times 3, that's negative 6. Negative 6, right? Plus 7, that's a 1. Negative 2 times 2, negative 2, that's a 4. Yeah. Plus negative 2, that's 2. Next, negative 2 times 2 is a negative 4 plus 7 is a 3. I hope this is correct. Otherwise, only one number is wrong. No? Everything is wrong. So, on the third row, this is a pivot. So, we wanted to eliminate these things. After this, we're done. Right? Alright. So, let's see. Ano bang gagawin? E13, the pivot is in the third row. That's why there's a 3 over here. E13, anong multiplier? We wanted to eliminate negative 8, so we wanted 8. To eliminate the 3, E23, negative 3. Baba na tayo dito. Okay, first row. Okay, so up from here up to here, nothing will change. Right? 1, 0. Pero dito, you see, from here up to here, up to here, nothing will change kasi lahat ito ay 0. Okay? So let's just write 1, 0, 1. Next, 8. 8 times 1 is 8 plus negative 8, that's 0. Of course, that has to be 0. 8 times 2 is 16 plus 8, that's a 24. I hope we're doing this correctly. Well, we will see. Okay, so that's going to be 8 times 3. 8 times 3, 24, minus 3, that's a 21. Okay? 0, 1, negative 2. So I will just copy kasi again, lahat ito zeros na. Then of course, this will be 0 because that's the goal. Okay? Next. What's next again? So let's see. 8 times 2 is 16 minus 2. What should be that? No. Not 8. Sorry. Dito na pala tayo. Negative 3 times 2, negative 6, plus negative 2, that's negative 8. Negative 3 times 3 is negative 9 plus 2, negative 7. Of course, we're just going to copy the last row. So at this point, I stop because we are already in RR EF. I hope that you can see that we are already in RREF. Now remember, this column corresponds to the variable x of 1, x of 2, x of 3, x of 4, and x of 5. You can see writing down the linear system. Now this linear system is equivalent to the following linear system. X of 1 plus x sub 3 plus 24 x sub 5 equals 21. X sub 2 minus 2 x sub 3, right? Minus 8 x sub 5 equals negative 7. Then x sub 4 plus 2 x sub 5 equals a 3. The next step is to back solve this linear system. But this linear system, no, in RREF is not a linear system in its ordinary form. Why? Now, when we look at the variables x1, x2, and x sub 4, they are the leading variables in every equation. In fact, x sub 1, x sub 2, and x sub 4 are called leading variables. Why? Because they lead the equation from the left. On the other hand, the variables, by the way, let's just write x1, x2, x4. The remaining variables, which are x sub 3 and x sub 5, are called free variables. So let me just write it here. X sub 3 and x sub 5. Now, why are they called free variables and the others are leading variables? Well, x sub 3 and x sub 5 are called free variables. Why? Because we can always assign any number to x sub 3 and x sub 5, and once we have chosen or once we have selected arbitrary numbers from x sub 3 and to x sub 3 and x sub 5, there we get a unique value for x sub 1, x sub 2, and x sub 4. Meaning to say, this implies that the linear system has infinitely many solutions because it has free variables. Alright, so what do I mean by this? So let's make a scratch. And how do we write the solution set? So here, I pasted down the resulting linear system. So, as you can see, if we let x sub 3 to assume a value of, let's say, r, and x sub 5 to assume a value of s, no, because they are not necessarily the same, then from these equations we can say something about x sub 1, x sub 2, and x sub 3. For example, x sub 4 should be what? 3 minus 2x sub 5, therefore that's 3 minus 2s. Also, from the second equation, ano sabi ng second equation? X sub 2 should be negative 7. Oh, is this a plus or a minus? Yeah, a plus 2x sub 3 minus a plus 8x sub 5. So, ang ginagawa natin, pinapalitan natin, pinililipat natin sa kaliwa, mula sa kanan, mula sa kaliwa, papunta sa kanan. So, ito, pwedeng isulat minus 7 plus 2r plus 8s. From the first equation, we get x sub 1 as 21 minus x sub 3 minus 24 x sub 5. Therefore, that's 21 minus r minus 24s. Is that correct? So, therefore, we can now write the following: x sub 1, x sub 2, x sub 3, x sub 4, x sub 5 equals, right, x sub 1 is 21 minus r minus 24s, right? Comma, x sub 2 is negative 7 plus 2r plus 8s. X sub 3 is r. x sub 4 is 3 minus 2s, and x sub 5 is s. We were just going to write r and s are scalars. F could be r or s or c. It depends on the situation. So in this case, this is what we call as the general solution, as it gives us all of the solutions to the linear system. So if we assign particular values for r and s, for example, if I say give me 3 solutions, so you're going to give 3 arbitrary values for r and s and then produce solutions. For example, if r is, let's say, 0 and s is 0, what does it say to the solution? Right? What does it say to the solution? It becomes 21, negative 7, 0, 3, and 0. So this is what we call as a particular solution. Particular solution because we give particular values for r and s. There are infinitely many particular solutions. And the general solution is written in parametric form like this. Alright? There. So what we can say, or what we can conclude, is that the linear system has infinitely many solutions. Okay? Alright, so we have seen cases where a linear system has a unique solution. We have seen a case where a linear system has no solution. And we have seen a case where a linear system has infinitely many solutions. For this next example, I would like to introduce to you a software that we can use to solve a linear system like this. Now, here I'm going to introduce to you Scilab. Now, Scilab as our tool. No, Scilab. Let's write Scilab. Pina-download ko sa inyo ito, right? So the first step, before we use the Scilab, the first step is to write the augmented matrix of this linear system. So the augmented matrix is going to be 3, 1, 2, negative 1, 3, 1, 5, 2, 12, 4, 28, 6, 2, 10, 4. So this is your augmented matrix. Now, how do we input this in Scilab, and how do we perform? The Scilab helps us do the process of RREF. As you can see, the process is tedious by hand, especially when the linear system is big. But the Scilab allows us to make the RREF easier. No, it will give us the result. So let me first switch to the Scilab view. So there's the Scilab view. So here you can see the console, the Scilab console. We call this the Scilab console. To input the matrix, we will input it row by row. Okay? So we have to name the matrix, let's say A. No? Open and close square brackets. Okay? The first row is 3, 3, 12, 6. To input the entries, you just need to put a space between the entries in the first row. So 3 space 3 space 12 space 6. Alright? To enter the second row, you have to put a semicolon over here, no? Just to tell the Scilab that you are going to enter the next row now. So the second row is 1, 1, 4, 2. Semicolon for the third row. 2, 5, 20, 10. Last row, negative 1, 2, 8, 4. So when you press enter, you see the Scilab assigns a matrix to the symbol A. To get the RREF, you just type RREF in small letters. Parenthesis A, and then when you enter, it will give us the RREF right away. Na hindi tayo napagod. Ay, meron naman palang Scilab. Well, dapat marunong kayo gumamit ng Scilab, pero dapat marunong din kayo mag-RREF by hand. Kasi not all the time may Scilab kayo on hand. So, ito yung result. Babalik nyo lang yung imaginary line. Okay? For 2, then all of these rows are zeros. Question: Are we somehow bothered by the zero rows? Are we supposed to be bothered by the zero rows? Not really. You know why? Because the zero rows are nothing but what? They're nothing but equations of the form 0x plus 0y plus 0z equals 0. You know that this equation is true for all x, y, and z. So it has no conditions at all. In other words, in this linear system, these last two equations don't say anything, so you can just ignore them. Or they don't have conditions to impose. So you just ignore them. So the resulting equivalent linear system is going to be what? X equals 0, y plus 4z equals 2. So this is the resulting linear system. So here, the leading variables, what are the leading variables? Are x and y. The variables that are not leading are called free because you can assign values to them freely, but in this case we only have one free variable. So therefore this indicates that the linear system has infinitely many solutions because we have a free variable. Alright, so what do we do now? Okay, so we assign a value for z arbitrarily, let's say r. Okay, then from the second equation, y is 2 minus 4z or 2 minus 4r. And then from the first equation, x is just 0. So therefore, how do you write the general solution? x, y, z equals 0, 2 minus 4r, comma, what? And then z is r. And where r is an arbitrary scalar. So let's say I ask you to give me two particular solutions. So when r is 0, a solution is, let's say, 0 to 0. No? Right? When r is 1, for example, a solution is what? R is 1, 0, negative 2, 1. So this is another solution. So changing the values of r will change this particular solution. So when I ask for the general solution, you're going to give me this one. But if I ask for a number of particular solutions, you should be able to generate by simply changing the values of the parameters. Now you can check that all of these or each one of these is a solution to the linear system by trying to plug them in there. Okay, now I have a computer exercise for you. I want you to solve this linear system using the Scilab if you do have, no? If not, you can use your matrix calculators on your cell phones. Now, last, as an application, I would like to discuss polynomial interpolation. So the polynomial interpolation problem is stated as follows. So here we have a list of n points, x1, y1, x2, y2, xn, yn in the Cartesian plane where n is greater than 1. Also, it is given that the x-coordinates are distinct from one another. Okay? So the goal is to find a polynomial p of x of degree n minus 1 such that this polynomial is satisfied by the points. When you substitute, when you evaluate the polynomial at xi, it will give us yi. Geometrically, this is what we are really after too. You can imagine that these 5 points are points in the Cartesian plane. Kunwari, ito yung x1, y1, ito yung x2, y2, x3, y4, at y3, x4, y4, x5, y5. Magkakaiba yung mga x. What we wanted to do here is to find a polynomial of degree 5 minus 1, which is a polynomial of degree 4, that passes through all of this. We wanted to find the polynomial function. Right? So this is the required polynomial function that interpolates these points. So the question is, how do we find this polynomial? Now, suppose that this polynomial is degree n minus 1 and it interpolates the set of points. So if it interpolates the set of points, if we evaluate each one, no, I from 1 to n, that should equal to I from 1 to n. Ganito yung lalabas niyan. Ito yung P of x sub 1, in-evaluate si P sa x sub 1. Ito yung P of x sub 2, in-evaluate si P sa x sub 2. Ito yung P of x sub n, in-evaluate si P sa x sub n. Ito yung lumabas, y1, y2, yn. As you can see, we wanted to get the polynomial, right? So, since we wanted to get the polynomial, we are looking for the coefficients a0, a1, a2 up to an minus 1. So, the unknowns here are actually the a's, right? The x sub 1, x sub 2, x sub n in this system of equations are actually constants, given constants. So, we don't ignore the exponents. These are just linear equations. The unknowns are the a's, no? The constants are the x's and the y's. In terms of augmented matrix, ito yung kanyang augmented matrix, no? Ito yung column that corresponds to a0, a1, a2, an. Ito yung mga column of constants yung nasa dulo. Mali. An minus 1. Because we just want a polynomial of degree n minus 1, right? So what we do from here, no, nakikita nyo yung x sub 1, ang first column nito laging 1, yung x sub 1 nandito, and then yung mga susunod na columns ini-square tas i-cube hanggang i-raise palaki ng palaki exponents. Yung x sub 2 naman dito nila, tas nandito yung y sub 1 by the way. Yung x sub 2 naman nandito, sa katabi niya yung square, yung cube hanggang maubos yung matrix. Sa kanan niya yung y sub 2. I think this is y sub 2. There's an error. This is a y sub 2. And so on. So then you just solve this linear system for a0 up to an using Gauss-Jordan method. So for example, we wanted to find a polynomial function of degree 3 that interpolates this set of 4 points. So, this is the polynomial of degree 3 where the coefficients are unknown and they are written as a0, a1, a2, a3. So, to set up the linear system, you just put a column of 1s at the beginning. Ito yung x sub 1 natin, x sub 2, x sub 3, x sub 4. So, first row, nandito yung x sub 1. And then, i-square mo siya, nasa kanan. I-cube mo siya, ito siya. Because ang y sub 1 ay negative 2, nandito yung negative 2. Okay? Ang x sub 2 ay 0. So, square mo man siya, i-cube mo pa siya, 0. Ang ka-pair niya na y ay 0 rin naman. So, yun yung method, no? Next, ang x sub 3 ay 1. So, 1 ito. Square mo siya, 1 pa rin. Cube mo siya, 1 pa rin. Ang ka-pair niya na y ay 0. Last but not the least, ang x sub 4 ay 2. Square mo siya, 4. Cube mo siya, 8. Ang ka-pair na y ay 4. And then we will just run the RREF. Now, I've made the RREF for you. You see, ito na yung A0, A1, A2, A3. That means to say that a sub 1, a sub 0 is 0, a sub 1 is 0, a sub 2 is negative 1, and a sub 3 is 1. And therefore, we get the following polynomial at your a0, a1, a2, a3. And when you simplify, you get this polynomial. If you want to check that this is correct, I've given the graph for you. So these are the 4 points in the plane. Ito yung 4. Nakikita nyo ba? Do you see? Ito. Pag graph ko yung polynomial function na x cubed minus x squared ba yun? Ayan. Ito yung lalabas. Okay? So I think that's all for this video lesson. And I hope to see you in the next one. Bye.